Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Meissner effect. Let's begin. In the year of 1993, two scientists, one named Meissner and another name was Wilkinson-Field. What was their observations? They took a material and apply the external magnetic field. That be the material. When the temperature is greater than to that of critical temperature. Critical temperature is that temperature below that critical temperature a material is achieved to its superconducting state, but in that of situation above that critical temperature, that is the normal state. In normal state, the applied external magnetic field or penetrates to that of material. When we cooled it under cooling means that the temperature is below to that of critical temperature, then what happened? In that situation, they observed that the lines of magnetic induction which are penetrates to that of material, these lines of magnetic inductions are expelled from that material. These lines of magnetic lines are expelled from that material when that temperature is below that critical temperature. At that situation, that material achieved its superconducting state. At that superconducting state we observed when we cooled that particular material below to its critical temperature. In that of superconducting state, we observe here that the applied external magnetic lines are expelled from that superconducting material, and that observation is our Meissner effect. We write what was Meissner effect. Thus, expulsion of magnetic lines from a superconducting material which when it is cooled below critical temperature, or we can say that is the transition temperature in a magnetic field. The magnetic field in a magnetic field is called Meissner effect. That is the expulsion of magnetic lines from a superconducting material when it is cooled below the critical temperature in a magnetic field is called Meissner effect. Two important aspects we observed from that of Meissner effect. One is that superconductor is a perfect diamagnetic substance. Superconductor is a perfect diamagnetic one. Here we see in Meissner effect the magnetic induction in that of superconductor is 0. The expression for magnetic flux, you have to prove it. We know the magnetic flux density B is equal to mu naught S plus I. whereas H, that is magnetic field intensity, I, intensity of magnetization, intensity of magnetization, mu naught, permeability of free space, permeability of free space. Then for superconductor, the magnetic flux density B is equal to 0. Therefore, 0 is equal to mu naught H plus I, or H plus I is equal to 0, or H is equal to minus of I. Therefore, magnetic susceptibility, the expression for magnetic susceptibility is Xi m is equal to intensity of magnetization to that of magnetic field intensity I by H. Here in place of H I substitute minus I, or in place of I substitute minus of H. Therefore, I divided by minus of I, which one is equal to minus 1. As magnetic susceptibility is equal to minus 1, that indicates the negative susceptibility is nothing but the characteristics of diamagnetism. Therefore, negative susceptibility is the characteristic of diamagnetism. In that case, a superconductor is a perfect diamagnetism. In that case, superconductor, here we take superconductor as B is equal to 0. Therefore, for superconductor is a perfect diamagnetism, diamagnet. One aspect, by taking the Meissner effect, a superconductor is a perfect diamagnetic is proved. Next aspect, the superconductor is a perfect diamagnetic, but that perfect diamagnetism of a superconductor cannot be explained simply by taking zero resistivity concept. In superconductor we know the resistivity is 0. If we take that zero resistivity concept, then we can't show the perfect diamagnetism of that superconductor. Means, in simple words, we can say a superconductor is different from that perfect conductor. Okay, let me show it mathematically. we know electric field applied electric field intensity is equal to applied electric field is equal to potential by distance V by L, where V potential, L be the distance, or E is equal to, in place of V, voltage is equal to IR from Ohm's law, from Ohm's law V is equal to IR. Now, to introduce that resistivity term, we have to multiply area both numerator as well as in denominator. Therefore, E is equal to IR by L, A divided by A, where A be the area of cross section. We rearrange the terms. As we know, resistivity is equal to RA divided by L. Therefore, IA, here RA divided by L is a term. That term RA divided by L is the resistivity, and I by A, current to that of area, is the current density. Therefore, E is equal to current density J, RA by L, resistivity rho. Therefore, J I by A, that be the current density, and rho RA by L, resistance, area divided by length, resistivity. E is equal to J into rho. For zero resistivity, E must be finite. Sorry, for zero resistivity, J as finite, so E must be 0. From that of expression, for finite value of J, current density as finite, and that resistivity as 0. Therefore, E should be 0. E should be 0. From Maxwell's equations, the curl of electric field grad cross E is equal to minus del B by del T. Here E as 0, therefore 0 is equal to minus del B by del T. Its differentiation is 0. Therefore, B is constant. B is equal to constant. What it indicates? It means that the magnetic field or magnetic flux through a perfect conductor does not change even if it is cooled to its critical temperature, and that is contradiction to that of Meissner effect. Hence, the state of zero resistivity as we taken, and in the previous section as perfect diamagnetism, these two are mutually independent of each other. what that particular expression indicates? It means that the magnetic flux through a perfect conductor does not change even if it is should be cooled to its critical temperature. And that is contradiction to that of Meissner effect, and we show it. The perfect diamagnetism of a superconductor can't explain simply on the basis of zero resistivity, which is contradiction to Meissner effect. From Meissner effect, we say a superconductor is a perfect diamagnetism, but here by simply taking zero resistivity we can't show it is a perfect diamagnetism, or in another words we say superconductor is a different thing as perfect conductor. Okay. And zero resistivity as well as perfect diamagnetism, zero resistivity and perfect diamagnetism, these two are independent with each other. So here with the help of this video lecture you understand the concept of Meissner effect, two aspects from that of Meissner effect. One is superconductor is a perfect diamagnetic. We saw how superconductor is a perfect diamagnetic. Next aspect, the perfect diamagnetism of the superconductor can't be explained simply on the basis of zero resistivity. By taking zero resistivity, we can't explain that superconductor is a perfect diamagnetism. That expression indicates the magnetic flux through that of perfect conductor does not change even if it should be cooled to its critical temperature, which is contradiction to that of Meissner effect, and it shows a perfect diamagnetism of the superconductor can't be explained simply on the basis of zero resistivity. Two aspects of Meissner effect and their proofs in form of mathematical way is given to you. So, with this useful and informative notes, let me wind up this session. Thank you.